This we've already looked at. So we've already looked at trends in reactivity, in particular of metals. We've talked about conductivity and why things are conductive. We've briefly mentioned the metallic bonding model, but we'll go into that a little bit more. Common properties of metals. Lustrous or luster, what does that mean?
Shiny.
It means shiny, right? Ability to reflect light. What's malleable?
Bendable.
Right, so bending or rolling into sheets. Ductile, what's that?
Drawn into a wire.
Drawn into wire. Heat and electrical conductivity. What property of a substance allows it to conduct electricity? Free flowing charged particles, right? I really want to emphasize charged particles, not specifically electrons, right? So it's electrons in metals, but when we go into talking about ionic substances, when they're dissolved in water, it's the ion that is able to carry the charge. So free flowing charged particles. In the case of metals, it's electrons. Reference to the nature of metallic bonding, we'll talk about that. Structure of metallic crystal. So we use the term crystal and lattice often together. What does the word lattice mean? Do you know? So when you think of lattice, what do you think of? Say a lattice fence. What does that look like? It's a grid, right? It's a regular pattern. So a lattice structure refers to a regular arrangement. Yeah. So crystal and lattice often go hand in hand, including limitations of representation. So we're going to talk about the limitations of the metallic bonding model, general differences between properties of main group versus transition. Transition is that big block in the middle. Our main group metals, group 1 and 2, and group 3 and the others, right? Experimentally determine reactivity of metals with water, acid, and oxygen, right? We've done water with our group 1, and we can look at our, sort of going to glaze over that a bit because we talk about reactivity again in Unit 2 in greater detail. Extraction process, that's something we're actually going to glaze over because it's not that important. For Unit 4, we do look at electrolysis of a metal in Unit 3, but that comes up later. The type of extraction process we look in Unit 1 is not all that important. Experimental modification of selected metal, we will look at that. Heat treatment and alloys. Properties and uses of metallic nanomaterials, we will go through that just mainly for interest, partly because that nanoscience, as interesting as it may be, is not in that 3-4 curriculum. So we are structuring the course to provide you with the skill set and the knowledge to best prepare you for Year 12. So what are metals, right? We know that they have high melting and boiling points. They have low ionization energies. What was that? What's ionization energy? Yeah, Lisa? Right, how much energy is required to remove an electron? So it's got low ionization energy, meaning that relatively low amount of energy required to remove those electrons. They also have low electronegativity. What was that again? What was electronegativity? Someone else? Right, the pulling power, yeah? The ability of an atom to attract an electron. They're generally malleable, ductile, conductive, and crystalline or lattice structures. When a metal loses atoms, so they lose atoms, they are always form cations. There's no negatively charged metals that I know of. There are thoughts about metallic hydrogen, but that is really only theorized and hasn't been brought into fruition yet. So the properties of a substance tell us something about the substance. They are strong, they are hard. Hardness is a measure of resistance to be able to be scratched. So the harder the substance will scratch a softer substance. The harder substance we know in general use is diamond. Right? So nothing will cut diamond other than diamond itself. Strong refers to its ability to hold a load. So more than 80 different metal elements. High densities, right? So coming back to that, one of those first things we looked at in the first week. Density equals mass over volume. High density means that the particles are closely packed together. Strong and hardness refers to how strong those particles are held together. Our exception to the rule is mercury. One of only 2 liquids on the periodic table at room temperature, the other being bromine. Mercury, minus 39 degree melting point, except it's very, very dense. In fact, if you had an entire bucket of mercury, you could stand on top of it. Don't recommend it, given the high level of poison that mercury is. Mercuric oxide used to be used as part of a liner on hats, and that's where you get the term Mad Hatter from, because leaching through the skin, poisons, deposits on the brain, makes you go mad. All of our different uses of metals link with the property, right? So building structures, carrying loads links with the strength, the lightness and strength, again, linking that to sailboats, aircraft, vehicles, and so on. Ability to form wires, right? And conductivity. Cabling for bridges or electrical works or dentist wires and so on, jewellery. Electricity is transmitted, so industry, domestic, computers, DVD players, so on, mobile phones. Diverse objects can be moulded and shaped, door handles, locks, shopping trolleys, school desks, jewellery, and so on again. So all of our different uses of metals all link back to its property. The model, as we pointed out, it's a positive metal cations. The positive ions, also called cation, nice way to remember it, is that there is a positive in the word itself. Or if you think cat and paw, cats are positive. 3D lattice structure, lattice meaning regular arrangement. So we've got this metal cation, and then surrounding that is a sea, often called a cloud, of delocalized electrons. If we think about the word local, local means here, right? So delocal means away from here. So the delocalized electrons are going to be those outer shell electrons that are loosely bound to those metal atoms and are free flowing. They're still attracted towards one another, so as they move, they will be attracted towards the positive ions and move around. So using this model, we can help to explain those different properties of metals. High melting and boiling points. Strong electrostatic force of attraction. So static means still, electro means charged, so it's a still charged base force of attraction. So the positive metal cations, considered from a mass point of view, much more significant in mass compared to electrons. So they're not likely to move readily. But the lattice or the metal is held together strongly by that force of attraction, opposite charges attracting. In fact, when it comes down to it, all bonding in chemistry relates to electrostatic in some way. So in terms of metals held together between metal cation and delocalized electron. when you think about the bonding within covalent. It's the bonding between the shared electrons and the nucleus of the atom. When you think about ionic bonding, it's the electrostatic force of attraction between alternating charged particles. So even our bonding between molecules is electrostatic. When we talk about dipoles, that idea of opposites attracting. Electrical conductivity, again, linking back to this idea about free moving charged particles, and it's the electrons. So they are repelled away from the negative electrode and move towards the positive electrode. Malleability and ductile come back to this idea of the bonding again. We put a force to the metal. So if this is my metal lattice and I apply a force to, say, that layer, it's going to shift across, but the lattice will be held together, right? So we can see that the shape of the metal moves as layers slide over one another, but they don't break. The lattice is still held together, but we can shape it. The limitations are that using the model, we can't explain the variability of the different properties. So we can't explain why mercury has such a low melting point compared to other metals that are really high. We can't explain the differences in conductivity. So we've got things like zinc is a fairly poor conductor, and zinc's actually used in dimmer switches. So what you're doing as you're dimming that is you're actually increasing the length of zinc that the electrical circuit's going through. Longer piece of zinc, we're increasing the resistance, you're decreasing the amount of current going through the rest of the circuit. Decrease the length of zinc, you're increasing the current that goes through the circuit, and you have brighter light bulbs. The metallic bonding model, none of this can explain the magnetic nature of some metals. Not all metals are magnetic. You'll notice that coins are not magnetic, and that's because they've been demagnetized. The positive and negative ions are scrambled throughout the alloy. Maybe I'll leave it there. I'll talk about alloys next lesson.
To a couple slides, please.
Yeah, let's just